Maybe it's because. Definitely not. All right, here we go. Continue Maclaurin series. Yeah, I would, but then this will be on your test, and then yeah. We talked about what it is, how to use it, how to write nth order polynomials, and even how to take composite functions and work with those. Today we're going to be talking about adding, subtracting them, dividing, multiplying them, and doing derivatives and integration with them. So when adding and subtracting a Maclaurin series, it is just like you would with normal polynomials. The resulting series will converge on the intersection of the intervals of convergence of the individual series. So what that essentially means is that, when you are adding, subtracting polynomials, you combine like terms, right? You'll do it a similar way with the series. So we're going to use cosine x equals the Maclaurin series for cosine x, and sine x equals what you see up there as well, the Maclaurin series for sine x, to write the terms of the Maclaurin series for the following up to x to the 7th. So I have sine x plus cosine x that I'm going to add together, and I'm essentially going to add the terms that are alike up until I get to the point of x to the 7th. So how do I do that? Well, I'm literally taking sine and cosine, their Maclaurin series, and adding them together. So that literally means, are there any other constants that get added in the sine function with the 1? No. So then I'm just going to have 1. Then I go to my next term, which would be my x term. Okay, I have x in sine. Do I have an x term in cosine? No. So I just add that. I don't have any other like terms to add together. And I continue this process. Do I have any other x squared terms? No. So this is going to be a minus x squared over 2 factorial. Yes, you could write 2 instead of 2 factorial, but since we're going all the way up to x to the 7th, and we see that x to the 7th has a 7 factorial, I'm going to leave it as the factorials instead of trying to figure out, okay, well, what is 7 factorial? And that's exactly what we do. We continue to add the terms that are alike. So that's going to be a minus x to the 3rd over 3 factorial, and x to the 4th over 4 factorial, and x to the 5th over 5 factorial, a minus x to the 6th over 6 factorial, and lastly, an x to the 7th over 7 factorial. Of course, this is a series, so we continue to write out the plus, so on and so forth, but I have successfully added my sine x and cosine x Maclaurin series. Now, yes, this is a simpler one, of course, but I didn't want to throw you into the deep end. But that's what you're doing. You're just adding your like terms. Okay? Here's another one. Same setup, still using cosine x and sine x Maclaurin series, but this time I'm doing sine x plus sine 2x. Okay? This one actually incorporates not only addition, but it also incorporates a composite. Okay? So if you did watch that video, I think I did a few more examples that dealt with the composite. What I'm going to do is I'm going to try to go ahead and find what the Maclaurin series is for sine 2x. So what does that mean? That means I need to replace the x in sine with a 2x. So everywhere I see a x in the Maclaurin series for sine, I'm going to replace it with a 2x. So the Maclaurin series for sine 2x is essentially what you see up here. I just replace all my x's with 2x. So then that's going to be 2x minus 2x to the 3rd power over 3 factorial plus 2x to the 5th over 5 factorial, and so on and so forth. What is 2x to the 3rd? 8x to the third. Let's go ahead and let's simplify this down some. Since I am going to have to combine like terms, I at least want my coefficients of my variables to be good. 8x to the third over 3 factorial. What's 2 to the 5th? And 2 to the 7th? So now to get sine x plus sine of 2x, I'm literally going to take all the terms in my Maclaurin series. I'm going to add them with the terms in my sine 2x to get my final answer. So x and 2x can be added together to get 3x. Then I have a negative x to the third over 3 factorial plus a negative 8x to the third over 3 factorial, which gives me and I continue to add, I'll have 32x to the 5th 5 factorial plus x to the 5th 5 factorial. And then since I'm going all the way up to x to the 7th, my last two is going to be a minus 129 x to the 7th over 7 factorial. The series does continue after that. You could continue to simplify this. Since you do have some coefficients here, 3 factorial is what number? 9 over 6 does reduce to what? 3 over 2? What's 5 factorial? Yeah, 5 factorial. Is there a number that goes into 33 that also goes into 120? What is it? 3. So that's going to be 11x to the 5th over 40. And then 7 factorial is 5040. Is there a number that goes into both of those? Probably a non-calculated problem. 129. So number that goes into 12, that also goes into 9.
Is that how that works?
It works for this one. So then that would be 43. And then 50, 40 divided by 3 is what? 1680. There you go. And that'll be your sum. All right. That I'm not sure. That had to be based off the mark scheme. So, but if it can reduce, of course, you always want to reduce it because you are adding. So, let's look at this next one. I have sine x squared, and then I have a minus cosine 3x. So this was a subtraction, so I've really got to be careful about that minus, that distribution. Not only that, I have a composite with a 3x and a x squared. So I need to be cautious. Let's go to the next page. Find me what cosine 3x is going to be, and we'll talk about sine x squared together. So for cosine 3x, we are able to replace, or able to use our composite and basically replace every x with a 3x. Okay, so then that would be 1 minus 9x squared over 2 factorial. 81 x to the 4th over 4 factorial. 729 over 6 factorial. X to the 6th, of course. However, the x squared, we actually want to be able to substitute in the x squared for each of our terms. And the reason why is because of the fact that it's our variables being squares, being raised to a particular power. When you think of the summation notation that represents the Maclaurin series for sin x, that square is going to have an effect on the exponent that's applied in that notation. So if you happen to have, was this on the video? I don't think it was. I think it was right before. I don't know if this one's on the video or not. Did you guys write down the Maclaurin series summation notation for sin x at any point? The summation notation for the Maclaurin series for sin x, we are going to have to use that here in order to find the series for sin x squared. The reason why, like I said, is because in general, to get each of these respective terms, especially with the exponent the way that it is, when we apply that x squared, it's going to affect the exponent within the series. So we have the sum from 0 to infinity. As we can see, our terms are alternating between positive and negative, which means that's going to have to be represented by a -1 raised to the k power. And then we have to represent the fact that we go x, then x to the 3rd, then x to the 5th. So how can we represent that? It has to be something in the general sense, because I just can't say +2. It has to be like every time I plug in a value for k, I'm getting the next term in the series. The next part will be x to the 2k plus 1. And now I need to represent my denominator. They go, there's no denominator, so that'd be 1. Then it goes 3 factorial, 5 factorial, 7 factorial. It's going to have to be something factorial. What's the denominator going to be? What is it? 2k plus 1 factorial. That's how we're able to get, if I plug in 0, that'll give me a 1 factorial, which is 1. I plug in a 1 for k, that gives me 3 factorial, plug in 2 for k, 5 factorial, so on and so forth. So if I replace my x with an x squared, that's going to be a power to a power here. And unlike when it's just a coefficient that gets plugged in, that exponent applies to the 3, the coefficient, and the x. Here, that squared affects my exponent altogether. So I have the sum from 0 to infinity of -1 to the k power. Then I'll have x squared being raised to the 2k plus 1 power all over 2k plus 1 factorial. And so how would I simplify that x squared raised to the 2k plus 1? 4k plus 2. Which means is when I find the terms in my Maclaurin series, they're not going to be what I would get if I were to plug x squared in for each of the x's into the original series for sin x. It's actually going to be something completely different. When I plug in 0 here, that's going to give me -1 to the 0 power, x to the 2nd power over 1 factorial. When I plug in 0 for k, what is that? When I plug in 0 for k, what does that simplify down to be? X squared. Plug in 1 for k. When I plug in 1 for k, that's -1 to the first power, which is, so it's going to be a negative. When I plug in 1 for k into the next part, that's going to be x raised to the 4 times 1 plus 2. So what's that? All over 2 times 1 plus 1 factorial. Now, if I were to plug in 2, that's going to take me to a term that my exponent for my variable is going to be larger than x to the 7. So technically, I don't need the rest of the terms because I have what I need to add, or is actually subtract, sine x squared from a cosine 3x. So what we're going to do is I'm going to take sine x squared, which is x to the 2nd minus x to the 6 over 3 factorial plus the series, and then subtract this series here, which was cosine to the 3x. So when I subtract the 2, what's my first term going to be in my series? It's going to be a -1, because I distribute the negative over to the 1. Then the next set of terms are going to be my x squared terms. I have an x squared here, and then a minus a negative 9x squared. The subtraction sign will be distributed. And actually, let me rewrite that over here in purple. I actually have an x squared minus a negative 9x squared over 2 factorial, which is 2. 2 negatives make a positive. The only way I can add x squared to a 9x squared over 2, which would be what? And when I add together, it gives me an 11x squared over 2. We have to go all the way up to x to the 7. My next one is pretty simple though, because my next one is an x to the 4th, and I don't have an x to the 4th over here. So all I have to do is make sure I distribute the negative over. So it's going to be a -81 x to the 4th over 4 factorial. What's 4 factorial? Is there a number that goes into 81 that also goes into 24? Y'all both said 8. Y'all both said 8 simultaneously. 3. What's 81 divided by 3? So that's 27 x to the 4 over 8. Good stuff. And the last term that I'm going to add together is going to be the negative x to the 6 over 3 factorial, which is then a minus a negative 729 x to the 6 over 6 factorial. Negative and negative make a positive, so I'm adding a positive 729 x to the 6 over 720. Add those up and reduce and tell me what the last term is of my series. So when I add the pink, that ends up being negative 120 x to the 6 over 720 plus 729 x to the 6 over 720. That reduces to be a positive or negative. A positive 203 over 240 x to the 6. Anything after that would produce a term that's bigger than x to the 7. And then that's how we would subtract sine x squared from a cosine 3x. So when it comes to adding and subtracting, you just want to make sure that you are combining your like terms and simplifying, okay? Now, when we differentiate or integrate, we would do so like how we would with a polynomial function, term by term. So we're going to take the Maclaurin series for cosine x, which is here on the board already. And we're going to find the Maclaurin series for sine x by differentiation and through integration. So differentiation, okay? What we can do is use our knowledge of the derivative of cosine to help us in finding the Maclaurin series for sine. Now, granted, we already know what the Maclaurin series is for sine already, so this will be more like of a show type of problem. The next, after we get through differentiation and integration, we'll actually do like a different problem that incorporates the two. So, what is the derivative of cosine? Negative sine. So we know that the derivative of cosine is equal to a negative sine x, okay? And so what we can do is sorry, messed up something. So since we know the derivative of cosine x is equal to a negative sine x, and sorry, I messed up on my notation here. Since we are trying to find the series for sine x through differentiation, we essentially need to solve for sine x here. So since the derivative of cosine is a negative sine x, I can rewrite this as negative d over dx cosine x is equal to a positive sine x. What this allows me to do, remember the notation for derivative, one of the notations is d over dx. What I can do now is I can replace cosine x with the Maclaurin series for cosine x and then apply the derivative of that Maclaurin series. So I'm going to replace cosine x with the Maclaurin series given. And now I can proceed to take the derivative of this series. Now, if you're, or this notation, now if you're like, well, how do I take the derivative of a sigma? Well, we're going to do a couple of things first before we actually get there. For one, we should already know that when I plug 0 in for k into this function, the series notation, that's going to be -1 to the 0 power, x to the 0 power over 0 factorial. What does all that simplify down to be? A 0. What's -1 to the 0 power? 1. What's x to the 0 power? And what's 0 factorial? So it simplifies down to be 1. So what we can actually do is we can actually rewrite this a tad bit by saying I can pull out that very first term, which I get by plugging in 0 for k, and then rewriting the rest of the terms from 1 to infinity of my series. This will aid in me proving the Maclaurin series for sine x, which I used on the last problem, okay? Because we already know what it is. We discovered it using the series. Now we're trying to show it using differentiation, okay? Well, first off, at this point, we are going to take the derivative of each term. The derivative of a constant, which is the 1 here, is what? 0, okay? And then for this next part, what you should realize is that we get the coefficient of each one of our terms in the Maclaurin series from this part right here. that -1 to a power divided by 2k factorial, that represents the coefficient of each of our terms. And the sigma just represents us adding up every single one of those terms. So if you think back to when we first learned about derivatives, here's a simple one. How do I do the derivative of 2x to the third? How'd you get that? I do 3 times 2, and then I subtract 1 from my exponent, correct? We don't do anything to this original constant, right? So because we don't do anything to the original constant when we're taking the derivative, same rules apply here. So that summation, okay, I'm going to apply that negative over. That summation and that coefficient are affected. What is affected is the variable and its respective exponent. So how do I take the derivative of x to the 2k? What would I do? Say it again. I bring the exponent down to the front, and then I subtract 1 from your exponent. So then this becomes 2k times x to the 2k minus 1. Because now I've taken the derivative of each part inside this parenthesis. I took the derivative of 1, which gave me 0. Then I took the derivative of that summation. Again, the part that I boxed in orange represents the constant, which never changes when I take the derivative anyway. I just end up multiplying it by the exponent and then subtracting 1 from my exponent that is attached to my variable. So when I take the derivative of what's inside of the parentheses, the summation along with the part that's boxed in orange is my coefficient. When I take the derivative of any normal polynomial function, the coefficient isn't affected except when we multiply it by the new exponent. So we leave the coefficient how it is, and then we just apply the power rule to the variable with its exponent. The variable with its exponent was circled in yellow. I bring down the 2k, like I would, like how I brought down the 3, and then I subtract 1 from my exponent. So now I have this. Remember, we are trying to find the Maclaurin series for sin x using differentiation. And we're slowly getting there. We're slowly getting there. Okay? Now, what I can do is, since that was a negative d over dx, that's why it's a negative in front of this sigma, what I can actually do is I can actually combine this -1 that's out in front with the coefficient in the numerator already, because that's 2 -1s. -1 times a -1 to the k power turns into what? Think about it. Your laws of exponents was -1 times -1 to the k power. Say it again. Exactly. It becomes -1 to the k plus 1 power. The summation is still the same. The coefficient just got affected by the fact there's a -1 in front. I've applied it to the coefficient, the numerator of the coefficient. And then over here, I'll have 2k still times k to the 2k minus 1. I can continue to simplify this some more. What does 2k factorial break down to be? And so on and so forth, right? So that's what's in the denominator. Don't I already have a 2k in the numerator? What can I do to those 2k's? I can cancel them out. So then 2k minus 1 times 2k minus 2 times 2k minus 3 can be simplified to be what? Exactly. So this turns into 2k minus 1 factorial because I've gotten rid of the 2k's, and then I have x to the 2k minus 1. Yes, because that's where it was. We're almost there. It looks almost exactly like what we had, what we saw in the last example when we created the summation for sin x. The only difference is that k didn't start at 1. K starts where? It starts at 0. So how do we make it so that it starts at 0? Well, what we're going to do is we're going to introduce a new variable, and we are going to use that variable instead of k. You want to pick a variable? Doesn't really matter. W. Okay. So what we're gonna do, because we are basically at the point where we need to be. The only difference is right now is that it's supposed to be k equal to 0, not k is equal to 1. So I'm going to let our new variable, which was given to me as w, equal k minus 1. Okay. And so what that means is that I'm going to replace every k in my problem, except for that one. I mean, every k inside of like the summation with a w plus 1. So that's going to become the sum of w equals, well, every k. So that's going to be a w plus 1 equals 1 to infinity. A negative 1, w plus 1 over 2 parentheses w plus 1 minus 1 factorial times x to the 2 w plus 1 minus 1. When I simplify that, how can I solve for w in the bottom of the sigma? Subtract the 1 from both sides, so you have w equals 0. I have my infinity on the top. Then I have negative 1 raised to the w plus 2 power all over. When I distribute the 2 and combine like terms, what do I have? And then over here, I'm going to have x raised to the questions up to here? Now, the last thing, just to remind you, what was in the black is the Maclaurin series for sine. We essentially have everything exactly how it is, except w instead of k. And this part right here should just be a regular W. Right now, we have it as a W plus 2. So I'm going to change it just to a regular W. It's an old concept. It's an old concept. Like, what causes you to add exponents? The same base as being what? What's -1 to the second power? So technically, wouldn't this just, so then you're left with -1 to the W power, and that is our Maclaurin series for sine. We use differentiation and the Maclaurin series for cosine to prove sine. How does this apply to using derivatives with other Maclaurin series? Well, clearly this one is a little bit more involved because we're trying to prove something, we're trying to show something. But essentially, the main part that you really need to take away from this is what was located right here and in this line, is that when you do differentiation with the Maclaurin series, you're taking the derivative of each term just like you would if it were a polynomial. We just went a step further and applied it to show how cosine is sine through differentiation. We're not screwing with it. We're applying laws of math here. I'll do integration separately because we are starting to run out of time, but we are gonna do a problem that involves integration with a different series. And so some of the concepts that I'm going to use in this particular problem, I'm going to use in the video separate that you'll watch on how to use integration to show the Maclaurin series for sine using cosine. So we're going to use the Maclaurin series for cosine x to find the Maclaurin series for cosine squared x. After we do that, we are going to estimate from 0 to 1 cosine x squared dx to 4 decimal places. Okay, this is an estimate. Of course, we can plug this into our calculator to get the exact value, but we're going to find an estimate and we're going to use Maclaurin series to do this. So the first thing we need to do is, one, we need to use Maclaurin series and find out what cosine x squared is. So first off, for the first part, which I didn't label A for whatever reason, but that is the first part. What is the Maclaurin series for cosine x? I already got the sum part, I just need the rest.
Over 2k parentheses.
Cool. All right, so then to find cosine of 2x, not 2x, sorry, x squared, I'm going to replace every x in the Maclaurin series for cosine x with an x squared. So then that's going to become the sum from 0 to infinity of -1 to the k power over 2k factorial times x to the 4k. So now I'm going to use that to estimate the integral from 0 to 1 of cosine x squared dx. Okay? So how do I do that? Like so. I can replace cosine x squared with the Maclaurin series that we just found in part A. And remember your rules of integration. Okay? I'll take a simpler problem just like I did before. If I have 2x to the third and I'm asking you to find the antiderivative, what would you do?
Maybe add one to the exponent and then put it back to the denominator.
Does anything happen to the original coefficient? Does anything happen to that 2? Not when you apply the rule. The only thing that is affected or that changes when you apply the rule is the variable and its exponent. So again, very similar to differentiation, the coefficient that's represented by the summation and the negative 1 to the k power over 2k factorial, that can be pulled out of the integral. Because that's not going to change until after we, get the new exponent, divide, and then multiply, right? So I pulled out the coefficient for this particular series, and now I'm just left with the integral from 0 to 1 of x to the 4k dx. Yeah, because the coefficient is going to get multiplied by the new by the new denominator and everything after I take the antiderivative. So now I need to take the antiderivative of 4x to the 4k. What's the antiderivative of x to the 4k?
4k, well, 1 over 4k plus 1x to the 4k plus 1.
Very good. So again, coefficient is going to end up getting multiplied. So my coefficient, which is this, ends up getting multiplied by the new denominator, or my new exponent. And then remember, I add 1 to it. Then I just need to integrate that from 0 to 1. Fundamental theorem of calculus says I plug in which bound first?
The first one, 1.
I plug in the 1. When I plug in the 1, that's going to give me, sorry, let me rephrase. What do I plug it into? I'm plugging it into x. So that's going to end up being 1 over 4k plus 1 to the 4k plus 1 minus what I get when I plug in 0, which is 0. So I'm left with 1 over 4k plus 1 times 1 to the 4k plus 1. What's 1 raised to anything? It's just 1. 1 raised to the 5th, 1 raised to the negative 2nd. It's just going to be 1. So essentially, this is going to go away, and I'm just left with 1 over 4k plus 1. That's going to get multiplied to my coefficient. So then this becomes negative 1 to the k power over 2k factorial times 4k plus 1. Of course, with the summation notation. And that is what I use to estimate the integral from 0 to 1 of cosine x squared dx to 4 decimal places. I'm going to plug in 0, 1, 2, 3, as many terms as I need to so that I can get an accurate estimate to 4 decimal places.
What is an accurate estimate?
Well, I'm not gonna plug so many values of k, because after a certain point in time, this number is going to get really, really small to the point where it's outside of 4 decimal places. Like those numbers aren't even going to affect that 4th decimal place. All right. And also, it's an estimate. So it's another thing to keep in mind.
So as long as we get to the 4 decimal places, we're good.
Mm-hmm. Okay, so I'm gonna put that down so you know exactly where these terms are coming from. So if I plug in 0 for k, that's -1 to the 0 power, which is, so my numerator is 1. Then when I plug in 0 for k, I'm gonna get 1 factorial times 1, which is just 1. I'm gonna add that to what I get when I plug in 1 for k. Well, that's just 1. So I already know I got 1 point something. What's -1 to the 1st power? -1. Then I'm going to plug in 1 for k. So 2 times 1 factorial is just, you're right. Then what's 4 times 1 plus 1? 5. So this is technically -1/10. -1/10 as a decimal is what? So I got 1 minus 0.1. Gonna keep on going. Plug in 2. What's -1 to the 2nd power? Then I'll have 2 times 2, which is 4. What's 4 factorial? Then I'm gonna have 4 times 2 plus 1. What's 24 times 9? Or better yet, what's 1 divided by the product of those two? Is 144? It's 216. So it's 1 over 216. What's 1 divided by 216? Calculators, because I do have to do 4 decimal places. So somebody tell me what that is. What's 1 over 216? 4629. Okay. All right. Let's plug in 3. That's going to give me a -1 over 6 factorial, which is a 720 times 13. Somebody do 1 divided by 720 times 13. One over 720 times 13. Yep.
0.0005.
What number?
06. 8.10.
Okay. That 6 is going to affect that 4th decimal place. So I got to keep going. I'm trying to get to the point where when I plug in a number, the decimal is so small that it's not going to have an effect on that 4th decimal place. That 6 and that 8 are going to have an effect on that 4th decimal place. So this one should take care of it, this last one. So then I'm going to add 1 over 8 factorial, which off the top of my head, I don't know. Then 4 times 4 plus 1, which is 17. So in your calculator, do 8 factorial times 17 and tell me what 1 divided by that number is. And that point is not going to affect that 4 decimal places. So then I'm going to add 1 minus 0.1 plus 0.4629. I'm going to add up all of these numbers. And then I'll be able to get my approximation. There's a correction on this one. It should have been 0.0016,837. So to 4 decimal places, you should get 0.9029, I believe. No. There we go. My mistake. I wrote down this number wrong altogether. I think when you said I missed everything. So it's 0.00010683. So then I believe that's how I'll end up getting the same thing that you got, because that is the correct answer. So the main thing to take away from this is that the sigma part and the coefficient part, that -1 to the k power over 2k factorial, that is the coefficient. Whether we're differentiating or integrating, that coefficient is not affected. It is the variable and the exponent that are affected when you differentiate or integrate. And so when you work with a problem like we did in this particular problem, you can pull out that coefficient and just integrate how you normally would, being careful that you're plugging it in for x and not k. After that, you'll be able to approximate, you'll be able to do several things with it. Okay? Real quick, just kind of listen along for this, because really what Maclaurin series is, when you're multiplying or when you're dividing, when you're multiplying, you're still collecting like terms. You're going to multiply and then collect like terms. With division, you're going to multiply both sides by whatever the denominator is, and then essentially it turns into multiplication again. Okay? So it represents some function, some different functions. So essentially, like y equals a function divided by another function. You just multiply your g of x, whatever the denominator is, to both sides, and you're essentially multiplying like before. So I just really quick want to show you how to do that. And then I know I'll have to finish up independently of you guys, okay? So when you are multiplying, it says use the first few terms of sine x to find sine squared x up to x to the 6th. Sine squared x is nothing but sine x times sine x. So that means you're going to take the series and you're going to multiply terms together. And you're going to collect like terms until you get up to x to the 6th. Okay? So, of course, this continues indefinitely, but you're going to use the first few terms to get you what you need. Okay? So that means I'm literally going to multiply every number in my first parenthesis by every number in my second parenthesis. Okay? But I'm only going to use the first few terms to do this. Okay? I'm going to multiply x by every term. What's x times x? What's x times a -1/6 x to the 3rd? I just increased my exponents. What's x times a 120 x to the 5th? And considering that I only went up to x to the 6th, I'm going to stop there. Okay, of course, this is a series, so it's going to continue. Now I'm going to do a -1/6 x to the 3rd by every term up to x to the 6th in the next one. What's -1/6 x to the 3rd times x? I'm going to line up my like terms so I can add them when I need to. What's -1/6 x to the 3rd times a -1/6 x to the 3rd? And I'm up to where I need to be. So I can stop there. Now I need to multiply 1 over 20 x to the 5th by every term. What's 120 x to the 5th times x? Do I need to keep going? No. So now I have what I need so that I can multiply, or sorry, I have what I need so that I can have my terms up to x to the 6th. And all I gotta do is add at this point, add my coefficients. So I'm gonna get x squared minus 26x to the 4th, which is what? And then I'll just need to add the coefficients here. So that'd be 2 over 45. So then there we go. We would compare that with the expansion of this, okay? What you would do here is essentially you would multiply 1/2 or negative 1/2 to each of the terms in your expansion until you get to up to x to the 6th. And what you're going to actually end up seeing is that when you do that, they're actually going to end up being the same. They're going to actually end up being the same. Looking at one that's a division problem together is the last one. You have this here, and it's equal to x over sine x. It's the power series expansion. Use Maclaurin series for sine x to find a sub 0, a sub 1, a sub 2, such that it's set up in that respective format. Remember, with the division problems, as it was stated on the other page, I know it's kind of quick, but just follow with me. You take your denominator and you multiply it to the other side. So what you'll end up having is sine x times the summation from 0 to infinity equals x, like so, because we multiply both sides by the denominator. Since we know already that sine x is a Maclaurin series that goes x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. I'm gonna stop there. That's going to end up getting multiplied to this. That series is created by plugging in 0, 1, 2, and 3 for k and adding them together. When I plug in 0 for k, I'm going to get a to the 0 times x to the 0. What's x to the 0? So just little a to the 0, right? Plus, when I plug in 1, that's going to give me a sub 1 x to the 1st. When I plug in 2, that's going to give me a sub 2 x to the 2nd, and so on and so forth. I'm going to stop there because that's essentially what I'm looking for, okay? So from here, what we do, all this is equal to x still. We apply multiplication, and we're going to multiply each term over. So with division, it incorporates multiplication. So I'm going to multiply x to every term. That's going to give me a sub 0 x plus a sub 1 x to the 2nd plus a sub 2 x to the 3rd. But I'm going to stop there because I'm really only concerned about only a handful of terms. Then I'm going to do the same thing with this. What's 3 factorial? 6, okay? So I'm basically multiplying a negative 1/6 x to the 3rd by a sub 0. So that's going to give me 1/6 a sub 0 x to the 3rd. And more terms after that. Then I'm going to multiply x to the 5th over 5 factorial to every term. Am I missing a term? I don't think so. Oh, thank you. I am missing something though. If I continue to go and I'll use x to the 5th over 5 factorial, so what essentially we have is that we have x is going to be equal to a sub 0 of x plus a sub 1 x squared. And then even here, we're going to have an a sub 2 minus 1/6 a sub 0 x to the 3rd. We wouldn't actually be able to add those because they're technically not alike, like combined into one term. So then in order for us to figure out what x over sine x is, approximately, what I underline in the red squiggle is essentially these are equivalent statements. Therefore, this matches up with this. What's the coefficient of the x? 1. So that means that a sub 0 is equal to 1. These are equivalent statements. Is there an x squared on this side? No, so that means that a sub 1 is equal to what? 0. Is there an x to the 3rd on the other side? So that means that a sub 2 minus 1/6 a sub 0 needs to equal 0. What's a sub 0? It's 1. So I can replace that and multiply. So that means that a sub 2 is going to equal, and there you have it. For all x near 0, you found a sub 0, a sub 1, and a sub 2.